Okay, in this lecture, we are going to be starting a new chapter. I have to start this chapter before we solve more tutorial questions because most of the tutorial questions after this will be using the first law of thermodynamics, and I don't want to, just use the statement delta Q equals to delta U plus W. I don't want to just start using this like that. I would like to give you some preface or preface to how we got here and what it all means, right? So, this is a new chapter, first law of thermodynamics, introduction. So, first law of thermodynamics is the conservation of energy principle. Of energy principle. That means Q in minus Q out plus W in minus W out plus energy of the mass flowing in minus energy of the mass flowing out equals to U2 plus KE2 plus PE2 minus U1 plus KE1 plus PE1. Right? So this is conserving all the types of energy that we usually see in a system. Heat, work, energy of the mass flow is equals to the final internal energy plus the final kinetic energy plus the final potential energy minus the initial internal energy, initial kinetic energy and initial potential energy, right? Now we can write this statement on a by mass or a per unit time basis, right? Divide everything by mass and you get all the small letters, small q, small w, small u, or by a per time basis where you will get all of the dots, right? So if we have no mass transfer, which is what we are going to be dealing with for a lot of this course, but later on we're going to get mass transfer as well, and that is when things get tricky, right? If we have no mass transfer, which is what we have for now, that is a closed system, then we get q in minus q out plus w in minus w out equals to this quantity. For stationary system, that is, a system itself is not moving, change in kinetic energy will be 0 and change in potential energy will also be 0, which implies a final form of this law is or we can say delta Q equals to delta U plus W. This is capital Q. The reason this is plus is because this quantity will be negative, this quantity will be positive. Don't confuse yourself too much with the signs, just remember this formula. If you were to write it on a per mass basis, we will write it as delta Q equals to delta U plus W, or on a per time basis, delta Q equals to delta U plus W. Now let us solve a simple question. A rigid tank contains a hot fluid that is cooled while being stirred by a paddle wheel. Okay. Initially, the internal energy of the fluid is 800 kilojoules. So U1 equals to 800 kilojoule. During the cooling process, the fluid loses 500 kilojoule of heat. So the delta Q is minus 500 kilojoule, because remember, if we take the fluid to be the system, then the heat is going out of it. So since heat sign is just it is with respect to the system, it will be minus 500 kilojoule. If the fluid loses 500 kilojoule of heat and the paddle wheel does 100 kilojoule of work on the fluid, determine the final internal energy of the fluid. Again, simple application. So, minus 700 U2 equals to 200 kilojoule. Right. And let us do one more question. This question is quite an important one because it will tell us of work being a boundary phenomena that I talked about previously as well. And overall is just important. This is Naveen sir. Right. Consider a piston cylinder filled with air, fitted with two electric heaters, 100-watt each, and a 540 kilojoule per hour paddle wheel. Okay. And this is our paddle wheel. The air is heated using a stove which transfers heat at the rate of 18 kilojoules per minute. Okay. To the atmosphere through the cylinder walls. From the bottom of the cylinder. Okay. There is a 40-watt heat transfer from the cylinder air to atmosphere through the cylinder walls. Okay, and it is losing heat at a rate of 40 watts through the walls. The air inside the cylinder expands continuously and therefore piston moves at a rate of 2 mm per minute. Okay. The piston has a diameter of 15 centimeter. Okay, this is a really tricky question. Mass of the air in cylinder is 1 kg. Pressure is 100 megapascal. Consider everything inside cylinder as system, i.e. cylinder wall as system boundary. What type of system is it? Okay, we cannot say it is an isolated system because clearly energy transfer is occurring through the walls, right? So I would say it is a closed system. Show all energy interactions, calculate net heat transfer, calculate net work transfer, calculate rate of change of total energy of the air, how much would be the increase in internal energy in 1 hour of the air, calculate change in internal energy of the room in 1 hour per kg of air. Okay, so this is a very tricky question, so let's do it slowly. Work done, rate of work done by the heater. Okay, since we are considering everything inside the cylinder as system, that is cylinder walls as system boundary, heater is transferring work through the boundary. So So the work done by the heater is minus 2 into 100 because work is seen with respect to surrounding is minus 200 watt. The reason this is not as Q is because this is not a boundary phenomena, right? Also, heater work is electrical work. Always consider. Here, heater work is electrical work. Similarly, rate of work by paddle is given as minus 540 kilojoule per 60 seconds, or if we convert it into joule per seconds, we get minus 150 watt. Then some heat is being supplied by the stove, right? So this can be considered as heat because this is a boundary phenomena. This is happening across the boundary of the container, right? So Q in is equals to plus 300 watt. If you convert 18 kilojoule per minute to joule per second, which you will get it, and the rate of heat loss through the walls is given us as minus 40 watt. Again, this is heat loss because it is happening across the boundary. So, work done by the piston is P dV upon delta T. Why delta T? Because this is rate of work done. Remember, we have put a dot everywhere, right? Which means it is rate of work done. P V2 minus V1 upon delta T. Why is this constant pressure? Because the cylinder is again atmospheric pressure, right? Which remains constant. So this is a constant pressure work. The piston is against atmospheric pressure, so it is constant pressure work. Equals to P A into delta X by delta T upon, yeah. So what I have done here is I have converted delta V into A into delta X. Why is this relevant? If you remember, this is how we did the derivation of the initial P dV work formula. So the height by which your piston moves into its area gives us effectively this entire volume or the change in volume. So we can write delta V to be A into dx or A into delta x. As the piston moves by a distance of 2 millimeters per minute, we get P into A into 2 into 10 to the power minus 3 upon delta T. Now delta T can be taken as 1 minute because we are doing everything in a per minute basis. Delta X by delta T is given to us at 2 millimeters per minute, which is this. We are doing by 60 because we want to find work done by piston on a per second basis, right? So if we replace everything, we will get 58.9 watt. And the net rate of heat transfer will be Q in minus Q out, which is 300 minus 40 equals to 260 watt. Why did this not become minus minus? Because over here we are taking Q loss with sign, which means we are implying the sign of minus over here. However, this is not really important. You have to think of it a bit using common sense. Q out will always be always put absolute. My point is always put absolute values here, and then the signs will take care of themselves, right? Next, the net rate of work done is, so our heater did this much work, our paddle did this much work, and our piston expansion work does this much. So minus 200 minus 150 plus 58.9 equals to minus 291.1 watt. the rate of change of internal energy, delta Q equals to delta U plus W, which means delta Q minus W equals to delta U, or rate of change of heat energy minus rate of work is equals to rate of change of internal energy, or dE by dt, which implies dE by dt equals to 260 minus of minus 291.1 equals to 551.1 watt. Therefore, delta U in 60 minutes of the surrounding air is equals to 551.1 into 3600. 60 minutes means 3600 seconds equals to 1984 kilojoules. Right. I have one more question where we will see where the work done by the heater is considered as heat energy. Let's just quickly go over the concept again. If something crosses boundary of system, that is heat. So if we were to take the air inside the system, okay, let me just draw our heaters. The air inside the container as the system, then it would be incorrect to write work done by heater, because now this is not work done, it is heat, because the heater is providing heat through the boundary, right? Since the air is now the system, the heat crosses the boundary to get to the air. So now we can say it is heat supplied by the heater. Similarly, the paddle will cross the boundary to do work on it, which means it will be supplying some type of heat energy. But since that is unintuitive, you have to be a bit careful while solving it, right? So again, now this is not work, this is heat energy. So everything else remains the same, because again, the heat that we found before was crossing the boundary to get in and to get out, and the piston will always do PdV work. So everything else remains the same, only these two things will change. So that is pretty much the only thing that you have to be aware of while solving these types of questions. Though I have to tell you, they don't really ask them much. Maybe occasionally they'll ask them in like one quiz or like 1, 3, 4 marks of midsem. But as always, it is always good to have this clarity of what is going on, what is the distinction between heat and work. With that being said, we're going to jump back into questions that we said last tute that we'll not be able to solve because of first law. But now, since we have knowledge of first law, we're going to go back to solving questions.